collaborative research projects of the network with the pretentious acronym Flair, and you can already see what it stands for. All right, I want to start with a bit of context. We have a couple of researchers in the Stardust research network whose main research is not really related to small bodies, but we're collaborating on a secondary project within the network that is related to small bodies. I also have to prepare you by saying that the project is in a fairly early stage.
Excuse me, Kajak, if you want, you can switch on your camera. Thanks. Sorry.
Can you see me?
Yes, thanks.
Good. I want to prepare you by saying that the project is in a fairly early stage. So in addition to feedback regarding our methods and plans, we'd be happy to receive your ideas and suggestions as to where the project could go and which issues we could tackle if you feel inspired. The project is based on an idea that my fellow researchers Shubham and Belayo developed some time ago. They were inspired by the fact that the OSIRIS-REx and Hayabusa 2 missions lacked the ability to perform more than a few samplings of the surface, and so they conceived a landing that's based on a robotic arm. The idea is that the robotic arm could be used for multiple tasks. First, there is sample gathering. Given an electric power source, a theoretically unlimited amount of descent, landing, or sampling operations could be performed. Bigger and more mass can be gathered from the surface. Existing pick and place methods from the robotics field can be used along with a variety of interchangeable tools on the robotic arm. Secondly, the landing operation itself could be less dangerous with some degree of agility and extra precision lended to positioning the spacecraft among potentially a bunch of rocks. Thirdly, there's potential for one-legged locomotion across the surface of the asteroid for visiting multiple locations. There's a lot to explore here given the advantages that I've mentioned, but this project deals with a select few ideas surrounding a robotic arm-based lander. We explore the landing scenario using a robot arm-based lander in combination with a vision-based navigation and guidance system and gravimetry experiments for gravity field estimation. So we decided at the beginning of the project that we wanted to develop a simulation that we could use to study the landing scenario. So we've been developing that framework. In parallel, we've been conducting a literature study on how each of our main research projects ties into the robotic landing idea, looking for gaps in the scenario where we could individually add value in a way that also benefits our own main research projects. And in the last phase of the project, we'll use the simulator to analyze the performance of the robotic landing system and the subsystems. There's a couple of conceptual aspects of the simulator that we're still working out, but the main framework has been agreed upon. We're looking to have a visual simulation environment with synthetic images of an asteroid landing, a dynamic simulation of the robotic arm and the spacecraft, a GNC system with integrated computer vision, and some sort of model of the gravity of the small body. I want to talk in more detail about the simulator we have in development, as it's the main measure of progress we have so far. The simulator is tied together with the Python programming language. We're using Jupyter Notebook to set up simulation scenarios along with documentation of results and analysis. The generation of synthetic camera images is based on Blender, which is an open source rendering engine, as well as publicly available shape models of asteroids. The robotic arm is simulated using the Drake software library. and the mission scenario, along with the guidance, navigation, and control system, is simulated in Astro Sim. This is a byproduct of the research of one of our colleagues, also a Python library. We're putting it all together in a Docker-based Ubuntu Linux environment and using GitHub to collaboratively develop the software. Now, the reference simulation scenario that we're looking to develop to start with is the following. The target body is the Ryugu asteroid, and the simulation starts with the spacecraft hovering above the surface at an altitude of 100 meters. The robotic arm simulation will engage at a lower altitude down to landing. This scenario is really a placeholder for the time being and is expected to evolve as we converge on a scenario that is designed to answer more specific research questions. Now we can talk about progress on each of the subsystems of the simulation. So first, the dynamic model of the robot and the spacecraft. This is the work of my colleague Shubham. He has created a description of the spacecraft with the robotic arm in the unified robot description format, which is a standard that allows us to integrate this model with our simulation tools. The spacecraft has the mass and dimensions of the OSIRIS-REx spacecraft, with the inertia assumed to be of a cuboid with uniform mass distribution. And the robot arm was adopted from the ETS-7 mission. Regarding the visual state, or the visual side of the simulation, we can produce images of asteroids already, but for simulated landings, we'll need to look at ways to add details on the smaller scale. The image you see here is from our software, from Blender. And the viewpoint of this image is 10 kilometers away from the Ryugu asteroid, but a closer viewpoint would reveal a relatively flat-looking surface. Adding detail could be achieved with texturing the shape with high-definition images, or alternatively with procedurally added shapes and textures, but that has not been decided yet. Visual navigation system concept still has to be developed along with the implementation. The research questions that the visual navigation system is focusing on are still being formed. In fact, during this workshop, I have already observed some interesting aspects from other presenters' content, such as the optically degraded images and loosely flying particles in the footage of the Hayabusa 2 landing, the tracking of ejected particles from the Bennu asteroid, and the onboard mapping with SLEM from earlier today. And now, my colleague Shubham will take over the talking for the rest of the presentation due to reasons.
Yeah, thank you. I hope you can see my screen.
Yep, I can.
Perfect.
Yes.
So yeah, thank you, Karl. So yeah, we have, I'm continuing with the updates on the tools that we have developed and what we have done until now. So the next part is the small body dynamics. So the work until now has been mainly literature study, and we decided to go with 3 dynamical models: the Polyhedron model for the gravity field, which gives, for gravity estimation, which gives one of the highest accuracy. And then we move on to a truncated spherical harmonics expansion, which is accurate until the circumscribing sphere. And of course, then the simplest one is the 2-body approximation. Now these, as you go downwards, the fidelity of your gravity field estimation reduces, but the computational time also gets much better. So there is a trade-off there. The current strategy is to use spherical harmonics up to the circumscribing sphere. And within that, we use the polyhedron model. This is still something we are working out, and how to switch between the models and how to get a computational advantage if possible. The next update is on the dynamic simulator called Astro Sim. Tomorrow, Pelayo's talk will focus more on the details of this. I will just present some of the updates related to a Flair project. So the 4 parts are propagation, navigation, guidance, and integration with other blocks. For propagation, capabilities including solar radiation pressure, gravity models are completed and ready, and you can see some of the validation plots here. The navigation part is also ready. So for example, these are some of the plots from the filtering that we did during the workshop in Madrid, also online. And here we can see the state estimation and the residuals for that state estimation. The last part for the dynamic simulator itself is the guidance part. At the moment, we have a guidance, let's say, algorithm running with minimum fuel cost criteria, and it was validated for a moon landing scenario, but this is still currently under development to include more constraints and make it better. After this, the main part is, of course, the integration of all our work. So there are placeholders for it at the moment, but we are slowly filling it in. That's the hope. So, for example, Roberto is responsible for the gravity model that we will include. So from polyhedron to spherical harmonics to two-body model. At the moment, we do have points as gravity models working. Karl already talked about the camera images rendering and the navigation, optical navigation. I'm working on the robotics actuator dynamics integration and the constraint the end zone, that is during the landing. So at the end of the landing, the spacecraft should hopefully be stable. And Pelayo is, let's say, looking at the bigger picture with Astro Sim. So we had a plan in the starting of the project. We had, for example, the first work package was a literature study. Now we do the simulator development and so on. Was this correct? So at the moment, we are indeed in the simulator development phase. However, it was not exact. There were holidays in between that were not considered. So yeah, the holidays did not overlap, of course. And so we are 1 month, let's say, in the starting of the simulation development rather in middle of it. So this is, I think, something that we learned. Write down holidays while making a Gantt chart. It's helpful. And for future work, basically finalizing all the simulator development and start doing the actual experiments, which will show us the viability of this method, if it provides any advantages, and if so, what are those advantages with respect to gravity field modeling, transversing the asteroid using hopping, or helping the GNC system by relaxing its constraints. We submitted a poster. A poster has been accepted for the International Symposium on Artificial Intelligence and Space Robotics and Automation. This was supposed to be held in California, I remember, if I remember correctly, but now it's being done online. So this here we present our initial idea and the motivation for why a robotic arm should be used. So with this, I would like to basically end the presentation and hopefully delve into more discussions rather than us talking.
Okay, so